In the next few lectures, we're going to talk about the assignment problem and a particular way to solve the assignment problem. The reason we're studying this problem is because the solution technique is the Primal Dual technique, which is a powerful technique we can use for a lot of different problems. In this case, we're just going to use it for this particular problem. In the assignment problem, we're given a graph that's bipartite with node set V1 and V2 and edge set E. Recall that in a bipartite graph, there's no edge that has both endpoints in V1 or both endpoints in V2. We assume that the size of our node set V1 is equal to the size of the node set V2, and that's equal to n. In addition to this graph, we're given a set of weights for every edge. The objective intuitively in the assignment problem is to assign every node V1 to some node in V2 in such a way that the weight of this assignment is maximized. In this case, we describe an assignment by a matching. Our matching has size n, meaning that every node in V1 is matched to a node in V2. And the objective is to find the matching that has the maximum weight, where the weight of a matching is the sum of the weights of the edges inside of the matching. In general, we assume that there exists a matching of size n. If there isn't a matching of size n, then we say that the assignment problem isn't feasible. Here we have a particular instance of the matching problem. We're given the bipartite graph with node set V1 and V2 and edges. We're also given the weight of every edge. In this case, the weight of every edge is given in blue. We've also highlighted the maximum matching in this case, or rather the assignment solution. In this case, our assignment solution includes an edge of weight 4, an edge of weight 3, and an edge of weight 1, for a total weight of 8. So in this case, the objective function of the assignment problem is 8, or rather the optimal solution has value 8. It's straightforward to write the assignment problem as a linear program. In this case, we'll say that the optimal solution to this linear program is z. Our objective is to maximize the sum of the weights of the edges that we choose, subject to the constraint that for every node in our node set J, there's at most one edge adjacent to that node. Similarly, for all the nodes in the node set I, there's at most one edge adjacent to that node. This in fact induces a matching. Every node is adjacent to exactly one edge. Of course, we have the constraint that all these xij's are greater than or equal to 0. We can take the dual of this linear program, and we'll call the dual value w. The dual is to minimize a set of weights on the nodes. The node set I has a set of weights u, and the node set w has a set of weights v. The weights of the nodes in this case have to be greater than or equal to the weight of the edge across it. So if we have an edge ij, the sum of weight on I plus the sum of the weight on j has to be at least the weight of that edge. We won't go through the actual derivation of this dual, just note that this is the dual. We're going to use both this linear program and this dual as part of an algorithm that we call the Primal Dual algorithm. The Primal Dual algorithm relies on one property and a particular criteria to show optimality. The property tells us that we can adjust the weights on our edges, and this will result in the same solution. In particular, we're going to look at the weight of the edge and subtract the weight of each node that's adjacent to this edge to find some new weight, c bar. By injecting this new weight, c bar, into our linear program, we end up with a solution with exactly the same value that differs by only a constant. In this way, maximizing the original weights and maximizing the new weights is effectively the same problem. We're not going to prove this, but proving it is relatively straightforward. All we need to do is some algebra. The optimality criterion that we're going to use is a little bit more critical. You may remember this optimality criterion when we're working with directly linear programs. In this case, we say that if we can find some dual solution, u and v, and some primal solution x, so that the following conditions are satisfied, then we end up with an optimal solution. The first condition is that our dual solution is feasible. That is, the weights described by u and v satisfy all the constraints in the dual. Second, complementary slackness is satisfied. And if you don't recall what complementary slackness is, in this case it tells us that if we have our primal variable xij equal to 1, that implies that the dual constraint has to be met with equality. Or correspondingly, if a dual constraint is met with equality, that implies that our feasible solution is equal to 1. In this case, we know that x is going to be an optimal solution to the primal, u and v are going to be an optimal solution to the dual, and the objective value of both are going to be the sum of the weights in u plus the sum of the weights in v, our dual objective value. We could have equally written that our dual objective value and our primal objective value is the objective value of the linear program instead of the dual. For purposes of our algorithm, this is going to be a more useful expression. In the next lecture, we're going to use this property and this optimality criteria to develop an algorithm.